Hey there, everybody. Remember me? I haven't seen you in how long has it been now? Remember back when we'd start each class period looking up at the screen, looking at the map of the world, the United States, Wisconsin, how many cases of coronavirus there were? Remember, I told you how I'd washed the desks, mopped the floor every day. We started using those wipes to clean off the calculators. I put them in the goggle box. And then it got really serious and they sent us all home, which is where we are now and where we're going to stay for the rest of the school year. We're not going to go back. We're not going to get to do any more labs. I don't know what to do with myself when I don't have labs to do, when I don't have students to teach. Well, that's not true. I've got plenty to do around here. I hope that you're finding things to do. I hope that you are practicing your social distancing, that when you go out, that you've got a mask to wear, that you're washing your hands, and that you're staying informed. Each day I wake up and the first thing I do is I take my temperature because I'm paranoid. I'm a little bit worried. I did go out to the grocery store. Did I pick up anything while I was there besides my groceries? I've been doing it online, actually. I've been, going to Pick and Save, and I order online, get my groceries. They put them in the car for me. That's about as much as I'll go out to places, go out for walks in the neighborhood. So you might have a lot of questions about what's ahead. You might be wondering how we're ending the semester with grades. There's a lot of information that I'm finding out that as decisions are being made, I will let you know. This is the place to come to look on Google Classroom. I'll also try to send out emails to everybody that I can. Communication only works when it's two ways, so make sure that you try to get back to me. I'll try to get back to you. And check in here because what I'm going to do is post some videos and some other materials about the topics that we were going to be covering that we're not going to get a chance to. But, I've got so many video demonstrations, I thought, why not show you some of the labs that we would have done and try to put them in a context that relates to what's going on right now. So the first one that I want to look at, the first question that I want to look at is in the topic that we were going to cover, looking at how matter and energy are related, the relationship between energy and chemical reactions, how we measure the energy involved in chemical reactions, how we measure the amount of energy that's stored in different things like our food. And this thermometer here, every day when I check my temperature, why is it when you get sick, does your body get a fever? What's going on there? Why does your body get hot like that? What's the purpose of doing that? So I want to answer that question over a series of demonstrations, and I'm going to begin by showing you a little contest that we were going to have called the chemical clock, and then how we were going to adapt the chemical clock chemistry to looking at the effect of temperature on chemical reaction rates to get at the question, what really is temperature all about? And then we'll apply that to a real biochemical reaction that happens in your body and use that understanding to answer the question, why do we get a fever when we get sick? So, pay attention. Here I've got 2 cups. In each cup I have a mixture that's clear and colorless. This one contains some sulfuric acid and potassium iodate and starch, and this one contains sodium metabisulfite. Now the two are not reacting right now because they're in separate cups, but when I mix them together I'm going to start my stopwatch and then watch what happens. So I'll mix them together, start my stopwatch, give them a little swirl there, and after a specific time you'll see a color change, very sudden, very quick. Boom. Okay, so my timer says 8 minutes and 26 seconds. That's a little bit faster than I wanted the reaction to go. I want to slow it down. I want it to get at a very specific time, that color change. So what I'm going to do is work out the amounts of each of these mixtures to put into this cup and the amount of this mixture to put into this cup so that when I mix the 2 cups together and start my timer, the reaction turns blue at a specific amount of time. Okay, so the idea behind that experiment was to change how fast or slow the chemical mixture turned from clear to blue. You can make the reaction rate go faster or slower based on the amounts of each of the reactants. So in order to react, in order to make that color change, the reactants had to get together. When you think about the chemicals in the mixture, think about the molecules, they're all moving around, okay? And in order to react, they've got to collide with each other. They've got to get together. So the more molecules you have, the more likely it is they're going to collide with each other and get together and react. Just like the more people you have crowded together, the more likely it is they're going to spread the virus to one another. See how I did that? Made a little connection. So things go faster in this chemical reaction when you raise the concentration of one of the reactants. And what you had to figure out was which reactant would make the reaction go faster when you added more of it, when you increased the frequency of the collisions to make the reaction go faster. So the next step is to take that chemistry and use the same amount of material, so keep that constant, but then to change another factor. That's to change the temperature. In the clock reaction experiment, everything was done at the same room temperature. But then in the next experiment, we are changing the temperature of the reaction and using the same amounts of materials so that we can find out, can we make the reaction go faster or slower by changing the temperature? So let's take a look and see how that works. Our goal today is to use the same chemistry that we were practicing with in the last experiment with the clock reaction to see what happens to the reaction rate when we change the temperature. We're going to use 3 different temperatures: 0 degrees, which is cold, 15 degrees, which is cool, and 30 degrees, which is warm. So one of the things we're going to have to do is we're going to have to make water baths that are at those specific temperatures and keep them constant at those temperatures during the duration of the experiment. The other thing that we'll need to do is fill up test tubes with the solutions. Now, I've made the solutions A and B a little differently from what you used. The B solution is the same. The A solution has the A mixture that you had last time, the clear cup, and it also has the C mixture that was in the red cup. So that's what's in here. And what we're going to do is we're going to put those into tubes that are labeled A and B. We're going to use the pipettes to measure very carefully up to the line for each 1 milliliter, so that you're putting 5 milliliters of the A solution in the A tubes, 5 milliliters of B solution into the B tubes. So someone could be working on that, while somebody else is working on getting the temperature of each of those 3 water baths to be at the right temperature. Now the 0 degree one is easy. It's just going to be ice water. That's by definition 0 degrees Celsius. So we don't have to control the temperature of that one. The 15 degree one, though, it's a little bit cooler than room temperature. There's a cup of room temperature water that you can use, put a little bit of that in, and then you can take some of the water from the ice bath and put it in here and look at the thermometer and make sure that the thermometer says 15 degrees. If you need to warm it up or if you need to cool it down, use the water that you need accordingly. These 2 trays will be next to each other so that you can do that. Once you've got the temperatures in these to the correct level, then you can take the test tubes and you can put them into the water bath. That means don't pour them into the water bath. That means put them into the water bath so that they get to be the temperature of what that water bath is. So all the ones going into the 0 degree ice water will go into that cup. All the ones that are the 15 degree cool water will go into that cup right there. And we'll leave them in there for about 3 to 5 minutes until they get to the temperature of that water bath. Over here, the 30 degree water, it's a little bit warmer. So if you start with some room temperature water is about 20-something degrees. And if you need to warm it up a little bit, then you can use the cup, the beaker of warm water that's on the hot plate. It's not so hot that you can't touch it with your hands. There's a glove there in case you can't stand the heat. So just add a little bit, check to make sure that the temperature gets to 30 degrees. And then if you need to cool it down, add more of the room temperature water. If you need to warm it up, add more of this warm water. Now if the water level in here gets to be too much, you can take some out using the squeezy pipette and just put that in the sink, because when you put the test tubes in there, the water level is going to go up.
and you don't want it to overflow. So keep the temperature constant. Someone's got to keep their eye on this all the time, because while it's sitting there, it's going to cool off. So someone's got to keep making sure that this stays at 30 degrees. Someone keeps that one at 15 degrees. That one stays at 0 degrees all the time by definition. Once this is at 30 degrees, and you've got all the tubes that you needed to make made with the A and B solutions, these go in here as well. Now, after these have been sitting in the temperature bath for about 3 to 5 minutes, then what we'll do is we'll take out a tube of A and a tube of B, and we'll pour them together into a little white cup and start the timer. When it turns blue, stop the timer and record the time, like we did before.
Okay, so I don't have a video demonstration that shows you what the results look like, unfortunately. This is a case where we would have to do the lab and collect the data so that we could look at it together. So you're just going to have to believe me. I've done this experiment a lot of times, and the results are very consistent, but I know it's much more satisfying when you see the evidence for yourself. But what happens in the experiment is that first I send you back to the lab bench to do the room temperature experiment so that we know what the baseline is at room temperature. And then I tell you to do the cold experiment, and so at a lower temperature. And what we observe is that the reaction takes more time, so it's going slower. And then after we discuss that, we make a prediction what's going to happen when we raise the temperature. If the cold one goes slower than the room temperature one, then the one that's at a higher temperature we predict will take less time to react because it's going even faster. And so then we go back to the lab bench and we do the experiment and we confirm our prediction. So what's going on here? And what does temperature really mean? What temperature describes about particles is how much kinetic energy they have. That means how much energy they have for motion. The higher the kinetic energy of something, the more energy it has to move around. What temperature describes is how much kinetic energy particles have. So the higher the temperature, the more kinetic energy, and the faster the particles move. The lower the temperature, the less kinetic energy, so the slower they go. So temperature, lower means slower, and higher means faster. So in the reaction, when the materials are combined, they turn blue more slowly when the temperature is lower because the particles are moving more slowly and it takes longer for them to find each other, and they don't have very much energy of collision in order to get them to react. Raise the temperature a little bit and they're moving faster, and when they bang into each other, they have more energy to initiate that reaction. Raise the temperature even higher, and now the particles are really cooking. They're moving around a lot, and so they bang into each other more frequently and with greater energy, so the reaction takes less time. So the higher the temperature, the more particles are moving faster. The lower the temperature, the particles are moving more slowly. Okay, so now we have a way to look at chemical reaction rates using this clock reaction, and then we used it to show what happens to the rate or how fast a chemical reaction goes when we change the temperature. The next step is to try this experiment but using a biological molecule. And the molecule that I'm going to demonstrate is called catalase. It's a molecule that's found in the human body and also in other living things. And I'm going to demonstrate an experiment where the catalase is used in a reaction at two temperatures, a lower temperature and a higher temperature. And we make a prediction about what's going to happen to the rate. If the reaction with the catalase works the same way as it did in the clock reaction, we would predict that at the lower temperature in the experiment, the reaction will go slower, and at the higher temperature in the experiment, the reaction will go faster. So first I'll show you how we would do it in the lab. And then since we don't have the lab, I'll show you how I did it in my kitchen and what the results look like, and then we'll talk about that.
Anybody ever call you a couch potato? That's because potatoes and you have something similar about your body chemistry. Right here, this thing is called your liver. The job of the liver is to detoxify poisons in your body. There's something about the chemistry of your liver that's similar to the chemistry of a potato. They both have a chemical called catalase, and its job is to react with hydrogen peroxide. Its formula is H2O2. Sounds a lot like H2O for water, only hydrogen peroxide is a poison. Your body makes that poison as an accidental byproduct of respiration, the way that you get energy out of your food. Take a look at this liver right here. This is from a chicken. I'm going to pour some of this hydrogen peroxide onto the chicken liver. Watch what happens. Oh, nasty. Look, it's getting all fizzy and bubbly. That's because there's an enzyme, a molecule in the liver that reacts with the hydrogen peroxide and turns it into safe water and oxygen. Potatoes also have that same chemistry. They have catalase in them as well. And what we're going to do is a little experiment that looks at what happens when you change the temperature of the chemistry of this catalase enzyme. So when you go back to the lab bench, here's what you'll find. There's a hot plate with some hot water, a couple test tubes, and I'll give you a couple raw French fries to put into the test tubes. And then take some water and fill the test tubes with the plain water. Now one of the test tubes we're just going to leave out, and the other one we're going to fill with water and put into the boiling water on the hot plate for about 5 minutes or so until that gets as hot as the water in the boiling beaker. After this has been sitting for about 5 minutes, then what we'll do is we'll take this out and we'll take both of the tubes and we'll pour them into the sink. Don't pour out the potato, keep the potato in the test tube. So I'm going to pour these both out, and then into each one I'm going to pour the hydrogen peroxide to see which one reacts more. Now one of them has been sitting at room temperature, which is cooler, and the other one is coming out of a hot boiling water bath, so this one's hotter, a higher temperature and a lower temperature. And you should predict, think in your head, what you think is going to happen to that reaction. Which one of these is going to react more, which one is going to react less, and why.
Okay, since we can't do this experiment together in the lab, I'm going to do it here in my kitchen. I've got a potato slice here. It's at room temperature, and this one right here, I nuked it for about, half a minute or so, and I'm going to pour this hydrogen peroxide onto the room temperature one, which is at a lower temperature, and this higher temperature one, I'll pour the peroxide on that one, and then I'll show you what's happening in each of these two potato slices. So the one that has the lower temperature, you can see that there's some foamy fizz there. You can see that the potato is even rising to the top. It floated because there's so many bubbles sticking to it. Now let's look over here at the hotter one. Now the temperature is higher in this potato, but there's no reaction going on. Now how can that be? If in the experiment that I showed you before, lower temperature reacted less and higher temperature reacted more. In this experiment, lower reacts more and higher reacts less. So what could possibly explain this, and what does it have to do with why we get a fever when we get sick? Safe temperature. You know, I had to go out to Pick and Save to get that potato and that peroxide. I risked my life, people, to make that video for you. Just want you to know that. Okay, so what happened there? The lower temperature reacted, the higher temperature didn't. That is the opposite of what we predicted based on the results of the clock reaction experiment. Now, the reason why gets to the question, why do we get a fever? So remember, temperature describes how much energy particles have for motion. So I'm going to use my son's snowman here as an example. This is from when he was a baby. The stuffing has been rubbed off of it. So if we're at low temperature, it's like I'm rocking my baby very slowly. Not a lot of energy for motion. Baby's sleeping, right? Raise the temperature. I'm moving faster now. Got more energy for motion. Baby might be waking up a little bit, looking around, what's going on here. Raise the temperature more. Yeah, now we're really going. Now the baby's like starting to cry, right? And now I really get the temperature going, and I start really moving the baby around, and you know what happens when you do that to a baby. Don't ever do that to a baby. Babies break. And so do biological molecules, and many other kind of molecules too. They break when you get them moving too fast. When you move chemistry too fast, it breaks. Now, that's part of the reason why our bodies raise temperature when we get sick. One, because the chemical reactions that enable us to fight off infections, they will go faster. Chemical reactions do go faster when temperature rises. But also, we're trying to make the chemistry of the infectious agent break too. So it's kind of a race because you don't want to break yourself. You can actually overheat your body. It's called malignant hyperthermia. You may have heard of that. Sometimes people have an allergy to anesthetic when they go under for surgery, and their body temperature will rise very, very dramatically up to 110, 111 degrees Fahrenheit, which is fatal. Anything above 105, 106, getting up into that range, you're starting to cook your brain. It's not a good thing. So when our body temperature goes up, we're trying to cook those infectious agents, break their chemistry. Our body also begins to, its chemistry is going faster as well. The combination of those things is part of the answer. Why does our body raise temperature? We're trying to break the chemistry of the infectious agent and do a better job with our immune response. So that's the answer to the question that we looked at today. You may have heard about some other things in the news about the coronavirus and possible medical ways of dealing with it. The idea of using hydroxychloroquine, that's one that's been touted by many people, including our president. There's a reason why people think that it might be useful against the coronavirus, and it has to do with what happens to chemical reactions as it relates to pH, or the level of acid and base inside of cells. That's something that I can show you another time using that same chemistry of the catalase reaction with hydrogen peroxide. I can demonstrate what happens to that reaction at different levels of acid and base and give you a sense of what that's all about. But that'll be for another time. In the meantime, keep yourself safe and keep coming back here and look for updates. I'll tell you more about the kinds of things that we are missing out on right now in chemistry, but I still want you to know, and so that you can relate the chemistry of our class to things that are really happening in the world around you. And that's really the reason why we take chemistry class, isn't it? So let me know if you have any questions about the experiments or something that you want to try or you want me to try here on the screen for you. Maybe I can put together something using whatever I've got around the house. We'll see.